Good evening, everybody. First of all, I would like to thank the judging committee for inviting me to present at this venue. It's an honor. I am Alexander Zadorozhny, and I am representing IBM Research Haifa, Israel. This is a joint work with my colleagues, Sergey Wasserkrug, Sergey Zeltin, and Vladimir Lipitz. I will start with the introduction of the wastewater treatment problem. I'm quite sure that this problem is new for many of you. Then I will go over a Markov Decision Process framework. This is the framework that we use to solve the problem. I will describe a decomposition algorithm we developed for the solution, data mining challenges we faced during the project, and I will conclude with a one-year pilot we conducted at Lleida city, Spain. Wastewater treatment plant is a plant that designed to treat sewage. Sewage, sometimes called influent, is entering the plant at this point. It passes three types of treatment: physical, at these clarifiers, where a solid part of water settles down, and the chemical and biological at the reactor. You can see here bubbles. Biological treatment is actually done by the bacteria that is coming with the sewage. The activity of these bacteria is determined by the concentration of dissolved oxygen in the reactor, and this is determined by the big blowers at the bottom of the reactor. In addition to treat certain chemicals such as phosphorus, chemical reagents are added to the water as well. After a liquid line treatment, most solid part of water is going to the sludge line and undergo a digesting process for a long period of time, sometimes greater than 1 week. Here, the most solid part of water is loaded on the trucks and just take it off the plant. As a byproduct of the process, a gas called methane is generated and is coming to the gas line and used as an alternative source of energy. Part of water is going back to input for the additional treatment. Cleaned water, called effluent, is diverted to the closed river. Chemical and biological processes in wastewater treatment are quite complex. Mathematical models consist of a set of differential equations which cannot be solved analytically. There are several simulators on the shelf. Some of them are better in chemical modeling, and others are better in biological modeling, but there is no single simulator which will be the best in both biological and chemical modeling. If you will take a look on the technologies that exist on the market, there is no technology that optimizes the process end-to-end. There are some technologies that allows local optimization, but we know what is good local sometimes can be very bad in a global sense. And this is a gap that our project is supposed to close. Our objective is to find a policy that minimizes total operational cost, such as all regulatory constraints are satisfied. The framework that we used for the solution is the MDP framework, and I will briefly recall what it's about. CMDP is a 5-tuple, finite set of states, finite set of action, transition probability matrix, immediate cost function, and a vector of cost corresponding to the constraint. The main difference between MDP and CMDP are constraints. The very important term in theory of MDP called occupation measure. Occupation measure shows probability that the process stay in a pair of state action. This is very important for linear programming formulation. Later we will see that this is a formulation that we will be using, and this term is important for this formulation. We use discounted cost model. Discounted cost model is convenient from practical perspective, from the reason that by choosing beta and playing with it a little bit, we can emphasize interval of time or horizon that for which we want to find an optimal policy, and which part of the process we want to cut off. Optimization problem is defined as given a 5-tuple, find a policy that minimizes an objective function such that all constraints are satisfied. Back to 60s, we know that there is LP formulation for CMDP, and the optimal policy is deterministic for MDP, stationary deterministic for MDP, and stationary and randomized for CMDP when a number of randomization is upper bounded by the number of constraints in CMDP. There are several difficulties that we faced during the project. First of all, if we take a look on the simulation model, we will find more than 100 of variables that are required for model representation. But when we go to the plant, we find just several relevant for optimization sensors. Historical data is limited and noisy, and the transition probability matrix doesn't exist. I worked for many years on a theory of MDP. First things I have that given a transition probability matrix with probably some assumption about the structure, I have to prove something. Here, no transition probability matrix. And last but not least, all the constraints must be satisfied. We started with finding a solution for a first problem, dimensionality. Our first estimate was that we don't need more than 20 variables, but even given just 20 variables required for optimization modeling, and very rough discretization of continuous variable just using 2 to 4 intervals, we get to a huge state space of something like 1 billion states. It's impossible to solve efficiently. To resolve this problem, we developed a decomposition algorithm. The idea behind this algorithm is a time separation property. We noticed that processes in liquid line are quite fast. Sewage that come in at input can be at effluent after a couple of hours, but processes at sludge line are very slow. Digestion process can take more than a week. Therefore, what is interesting to sludge line at input, not exact value of the state at any given time, but the distribution of state values, and the output of a sludge line can be considered as a constant value. They are constant for a long period of time. Therefore, we can take a distribution of states at the input, and for other blocks we can we solve the problem separately per each constant value. There are just a few such values. Overall, the idea of the algorithm starts with discretization of an occupation measure, which represents a state at the input. Occupation measure shows a distribution of states. Then find set of locally optimal solution per each block, and last stage, find the cheapest aggregated policy. Very simple. We proved that our algorithm finds epsilon optimal policy. Epsilon optimal meaning that given a requirement that the solution must be at most epsilon from the optimal value, the algorithm must find this solution, and the runtime of the algorithm is pseudo-polynomial. This is what we could prove mathematically. After we have a decomposition algorithms, the runtime of the problem is actually bounded by the state size of the biggest block in our problem, and this is not expected to be more than 10, and it can be easily solved. At this moment, we felt quite confident to use CMDP for solution, and we started to looking for necessarily variables that must be in the model in order that optimization model will be meaningful. If we don't have enough sensors to sample a meaningful state, we can't solve the problem by this method. First variable that must be inside is influent flow. This is clear. If influent is 0, the optimal policy is just shut down the plant at zero cost. And if you'll take a look on influent flow a day after Christmas, the volume is huge and the treatment is very expensive. Feedback. It must be inside not because the volume is high, it is not, but the chemical concentration at feedback is very, very high, something like 10 times higher than at influent. Feedback can change chemistry of the water significantly. There are two variables which correspond to constraint. By empirical study, we got to conclusion that in order to satisfy all the regulatory constraints, effluent total nitrogen constraint and effluent total phosphorus constraint must be satisfied. When these two constraints are satisfied, all other constraints will be satisfied with great margin. We need at least one variable per each constraint, and we formulated it with exactly one variable. Time period need to be in a state space as well, from the reason the electricity tariff is changing during the day. There are 3 time interval. So the algorithm have to know the prices during the day, therefore time period need to be in a state variables. And the last but not least variable is total cost. This is somewhat not standard and even a counterintuitive. Normally, we see cost just an objective function, and here it appears in a state space. The reason that we did it to a reduced state dimensionality. Cost is a function of several variables. If we will put cost just in objective, then we have to put all these variables to state space, and it will be much higher. And it appears that this state representation is very successful, and we succeeded to model the problem using just 6 variables. And if you have only 6 variables for overall problem, there is no need to use decomposition, and we didn't use it, finally. And we keep it for much bigger plants. For 6 variables, we can just solve the problem optimally using linear programming formulation and running any method to solve it. But it wasn't unclear at the beginning, and without a trick that we did with the cost, it is unclear as well whether we can solve it directly or not. Action variables choice is straightforward. We got 3 controllers to work with, and we define a variable per each of these controllers. There are 2 pump controllers and dissolved oxygen set point controller. Total cost consists from electricity consumption cost, sludge disposal cost, chemical reagents cost, and the negative cost of electricity that produced using methane gas. There are 2 constraints, effluent total nitrogen and effluent total phosphorus. The only thing that is missing to define a linear programming problem is a matrix, is a transferability matrix. To estimate this matrix, we developed 3-stage heuristic. At first stage, we run coverage. This is a pretty long procedure. We ran it for something like 1 week, 24/7 on one of our laptops. And the end of this stage, we have a transition probability matrix. The problem with this matrix is that there are some entries which are 0 in this matrix, but they are not 0 in reality. To solve this problem, we developed a second stage called interpolation, where we interpolated missing values using values of existing neighboring states. The last stage is ensuring of irreducibility. Our assumption is that biological and chemical processes are irreducible. Mathematically, this simplifies the thing, since when irreducibility is guaranteed, we work with one connected component. Now we can define a linear program. This objective is the inner product of a vector of occupation measure and the vector of immediate cost. There are a set of constraints related to the transition probability matrices, where right-hand side is just the initial state distribution, and there are a set of constraints related to regulatory constraints. That's it. At this stage, we have all pieces of puzzle together, and we were ready to go to the plant and check how good our technology is. For this purpose, Lleida city, Spain was chosen. This is a medium-sized city, around 140,000 inhabitants. Objective was to reduce the total operational cost such that all constraints are satisfied. Our choice for a sampling period of MDP or epoch time was 2 hours. There are 2 main reasons why it's 2 hours. First of all, client didn't want to add overhead to his staff, and the request was 2 hours from the beginning. Whether it is good or not, we had to validate in simulation, and we made numerous simulation and optimization, checking short periods like 1 hour, and our conclusion was that 2 hours are good enough. Shorter periods didn't provide any significant benefits beyond 2 hours. Therefore, this is what we used. Operators followed policies that our system recommended 24/7 for 1 year. Here you can see a user interface that operator saw on their computer. There are 3 values corresponding to the set points of 3 controllers. Every 2 hours, operator come, press refresh button, and see new recommendation set points. There is additional value for the actual dissolved oxygen concentration in the reactor. It was just to help the operators to set a new set point precisely. Based on feedback we obtained, follow the recommendation was very easy during a pilot period. Result that were achieved during the pilot is a 12% reduction in electricity costs related to the aeration, a 35% reduction of electricity consumption related to internal recycle pump, roughly 20% reduction in sludge production, 14% reduction in chemical dosing reduction. In addition, quality of water was improved, specifically at the efficiency of total nitrogen removal. This thing a little bit more difficult to quantify. This is quality. This is not a cost. Cost percentage, okay, it's very, very clear. This is very difficult to quantify. When I discussed the results that we obtained with the plant manager, he emphasized that for him this is even more important than these results. Actually, the goal of this plant, what is built for, is to clean the water. If it's not for sufficient quality, what did we do? Here I want to tell you a short story. A week before the actual deployment, we were running simulations and saw a cost reduction of around 12 to 13%. We saw that all the constraints are satisfied. So we were quite certain that we will improve something. We're not sure how much. Since one thing is simulation, other thing is a real plant. Not everything is perfect. As opposite to us, the client was quite skeptical. How a few guys from IBM, using something called operational research, can manage the plant in a more efficient way that they do, and they are expert in this domain. We are not. First time I heard about wastewater treatment plant problem, it was at the beginning of the project. I'm not an expert in this domain. They knew this too. 2 weeks after the deployment, situation was completely different. Suddenly they saw 20% reduction in sludge disposal. Namely, you need to order instead of 5 trucks, 4 trucks. It's a significant difference. Suddenly they have too much chemicals in their stocks. What to do? And they had some chemicals on the way. Where to store this? At this point, the attitude of the client to what we are doing changed, and they followed our recommendation precisely. I remember this, and I really enjoyed this moment 2 weeks after the deployment to see the change in attitude. Quoting a plant manager, we can see that the change, actually the shift from static policy to dynamic policy provided much more controllability. They finally felt that they can really control the processes in the plant, and they can trust the system and invest their time in other things on the plant. They have a lot of things to do except controlling this process. The last but not least, the thing that they mentioned, this plant that they gave us for pilot was considered or already optimized based on this industry standard. So given this, if you go to a least optimized plant, the results are expected to be even better. I want to summarize my talk by 2 bullets that I think the most important. First, impossible, sometimes possible. I mean by an impossible, at the beginning we had curse of dimensionality, what to do. Then we had not perfectly calibrated model. It appears to be the reality to get a perfectly calibrated model is visually impossible, or it's that expensive that no one needs now technology. We had some difficulties, actually a lot of difficulties with data. At the end, it worked quite well. The cost reduction was significant, and in addition, the quality of water was improved as well. The development of this system based on a technology that we developed is quite complex. There are several languages that we had to use to code it. There are several tools that we used. And we had to use some architecture which will allow to us to actually to work smoothly with the client. It was IoT based. All this development took time and was quite complex. But what's important, the most important thing is client feedback. It was very easy to use. For me, it was like paper writing. We worked hard to write a paper, so the reader will enjoy it and will understand easily what we wanted to say in this paper. There are two topics that in progress. First is more precise constraints modeling. There are different types of constraints. Some hard constraints, some expected average constraint. In this implementation, we approximated everything with expected average constraints, and we had to take margins. At the moment we model everything precisely, we can remove the margins and decrease the cost again. The last thing is a hybrid estimation of traditional probability metrics. So far, all the estimation is based solely on the simulation model. What we want to do is to gather real-time data to improve it. So the process will be self-improving. Transition probability metric, this is something that describes the dynamics of the plant. Instead of all the differential equations that are modeled in simulator, we have a transition probability matrix. This is our plant. And improving its estimation can provide additional improvement in the results. Thank you.